So yeah, so I guess the purpose of me giving a colloquium talk is to reintroduce myself, since I was not here last year. So when I do have to introduce myself, I usually say that I'm a complex algebraic geometer, even though that's actually not really true. Because I'm actually a fairly simple-minded character with a quite straightforward personality. But so it's also not true, because what I really do is I use Hodge theory and apply it to complex algebraic geometry. So Hodge theory is really, at the base of it, it's some theorems about elliptic differential operators on manifolds, right? So at the bottom of it is just hard analysis. And the truth is that algebraic geometers are very good with algebraic formalism, but they're somehow not very good with this kind of hard analysis. So for the algebraic geometer, what Hodge theory does is, it's like one of these thermos coffee pots, basically. So you can touch it on the outside and you don't burn your hands. You can carry it around, and then sometimes when you need it, you can press a button and dispense a little bit of stuff at the right time. So that's what it does for us. Okay, so what I want to explain today is just a specific, I want to talk about a specific example of how Hodge theory is used in algebraic geometry. And that's the story of this generic vanishing theorem. So this goes over a period of maybe 25 years or so, and I want to explain how it started and kind of how it changed over time. Okay, so let me start with the most famous vanishing theorem, which is the Kähler vanishing theorem, just as a reminder. So this says that if you take X to be a compact complex manifold, and then you take the positive line bundle, so L is a positive line bundle. So positive in the sense that the first term class is positive. So this, of course, will imply that if you have such a line bundle, it will imply that X is actually a submanifold of projective space with projective. And so in particular, it's compact Kähler. So this just in parentheses. So we were actually really talking about projective manifolds in this case. But then the theorem is that for every integer I, which is less than the dimension of X, you have this vanishing of these cohomology groups. Okay, so this is a typical vanishing theorem.
So actually the explanation of positive meaning that C1 of L is positive is going to just confuse people that aren't experts. Since that's not an inequality of numbers, and it's a partial ordering.
Yeah.
So that C1 of L is a Kähler class. Yes.
Right, so the
fact that it's Kähler you already see without using Kähler embedding, you see that it's compact Kähler because C1 of L is represented by Kähler.
That's so I guess I should say it this way. So this is really what it means, that it's actually positive in the same sense that a Kähler form is positive. Okay. And so the story of the generic vanishing theorem started in the late 1980s with Green and Lazarsfeld. And they were basically asking, so they were back then, they were both at UCLA together. And they started asking what happens when you take, instead of positive first term class, you take the first term class to be trivial. So you look at bundles with 0 first term class. And so more precisely what you want to look at is, again, we want to take X to be compact Kähler. And now these line bundles with trivial first term class, they come in a whole big family. Right? So there's a whole space of such things, which we denote by pigment of X. So this is the space of isomorphism classes of such line bundles.
So X is emphatically not simply connected here, right? So you want.
Yeah, that's right. But so in fact, let me say this here. So So this modular space, of course, if X is simply connected, it would just only consist of the trivial bundle, right? But in general, this is a compact torus of dimension equal to the dimension of the cohomology, the first cohomology of the structure sheaf, which in this Kähler case is 1/2 of the first Reed number.
And that's the complex dimension. So its
The
complex
complex
dimension is actually the first Reed number.
Okay, and so then the question is, when I take different L's in here, what does the cohomology look like, right? So before I tell you any sort of general theorems, let me give a bunch of examples that show what kind of things can happen, okay? So this first example will show that, in fact, different from the Kodaira theorem, there's no uniform behavior in general. So let's consider the case when I is equal to 0, the zeroth cohomology. So in that case, there's two different possibilities. You could have the line bundle be isomorphic to the trivial bundle, and in that case, it does have a section. So then the cohomology is just C. If the line bundle is not trivial, then because of this condition on the term class, there can actually not be any sections. Okay, and so we're going to use, since we'll be talking about this sort of behavior, I'll make a small definition here. So in general, I say, I look at the set Si of X, which is just the set of all line bundles where the cohomology is non-trivial. Okay, and so then we can say this statement up there by saying that S0 of X just consists of only the trivial bundle. Right? Okay. Another simple example shows that sometimes, in fact, all of these groups are non-trivial. So you don't always have vanishing either. So this is, suppose I take a curve. So let's see the compact Riemann surface of genus at least 2. And so then if I look at H1 of such a line bundle of degree 0, so in this case, this peak 0, the first term class is just a degree, so this is just saying that the degree is 0. In this case, I can use seriality and rewrite it as global sections of some other line bundle. So this is dual to the sheaf of differential times the inverse of this line bundle. And these two vector spaces are dual. And so here, in the case of a curve of genus at least 2, this is a line bundle of degree 2g minus 2, because that's the degree of the sheaf of differentials, and this line bundle has degree 0. And then just for degree reasons, this is always non-zero. Okay, and so in this case, the conclusion is that S1 of a curve is always the entire big knot of the curve.
So in the Kähler vanishing theory, you'd be ignoring the top dimensional one. This is the one that corresponds to the.
Yeah, that's right. So this would in this case also be the top dimensional, right? So this is sort of like the Kodaira theorem that says that in the top degree actually doesn't vanish. Okay. Let me also tell you a somewhat more complicated example. So again, X is compact Kähler, but now suppose I have a map from X to a curve. Okay? And then suppose that, so again, the genus of the curve is at least 2. And let's suppose that this map is what's called a fibration, so it has connected fibers. So this is holomorphic mapping with connected fibers. Which in algebraic geometry would say that if you look at the push forward of the structure sheaf, this is just the structure. Okay, so if you look at the functions along the fibers, they're just constants because the fibers are connected. So then in this case, if I take a line bundle on a curve of degree 0, I can pull it back to X, and I will get a line bundle with trivial first term class. And then if I calculate the cohomology on X, then this cohomology can be calculated by pushing it back onto C and calculate it on C. And if you analyze this, you find that this always contains a subspace which is just this, which actually, in the case of connected fibers, is just the cohomology of the original line bundle, which, by example 2, is always non-zero. Right? And so this shows that the set S1 of X, in the presence of such a map, it contains a copy of this big lot of C. And in fact, so there's a slightly more general result if one does this a little bit more carefully. So in fact, you can look at not only line bundles that come from C, but you can look at this slightly more complicated set, which is the set of line bundles on X that are trivial on the fibers, on the typical fiber, on the generic fiber. So L is trivial on the general fiber. And one can show that this also ends up sitting inside of S1 of X by a similar argument. And this set is actually, so this is a union of finitely many translates of pigment. Okay, so in some cases, if the fibers are not very singular, it's just pig knot, but if there are many singular fibers, then you can have some other components that are isomorphic to pig knot, but don't go through the trivial bundle, but go through some other bundle. Okay, so this is what I mean by translate. Okay, and there is in fact, in this setting, there's a nice theorem even. This is due to Bourvil and Campana, but which says that this set S1 of X is always, it always consists basically just of these things. So this is a finite union of sets plus maybe some similar kind of set in the case where you map to a curve of genus 1, plus finitely many points that are somewhat different, plus finitely many points. And these finitely many isolated points, they are similar to the kind of translates that you get here, in that they are line bundles of finite order. So it's line bundles so that some power is the trivial one. They have finite order. Okay, so this example, what it shows is that these sets, they have some structure, but the structure of the set somehow knows about some geometry of X. So in this case, the set S1 of X kind of remembers maps from X to curves. Okay, so now what did Green and Lazarsfeld do? So let me tell you a few results by Green and Lazarsfeld. So this is kind of the starting point of the whole subject. So I will tell you two kind of results, and then we'll see sort of over time how our point of view on these things has changed. So the first one is the so-called generic vanishing theorem. So before I can state it, I have to introduce one other thing, which is the so-called Albanese variety of X. So this is, you can write it down very easily. So it's again a compact torus, but you get it by looking at functionals on the space of holomorphic one form on X, modulo, so those are maps from this that take holomorphic forms to complex numbers, and then you take the modulo so-called periods, which are those functionals that you get by integrating over closed loops inside of X. Okay, so this is again a compact torus, which is actually dual to pig-knot. So it has the same dimension as pig-knot. Again, half the first little number. And the purpose of this, or the reason of looking at this, is that it comes with the so-called Albanese mapping, which is if you choose a base point on x, then you can look at the functional given by integration, which is well-defined modular periods. So this is the so-called Albanese mapping. Okay, so for example, in the case of a curve, this would be the usual embedding of the curve in its Jacobian variety. Okay. And so then the first result by Green and Lazarsfeld is that if you look at these sets Si of x, you can get a bound on their codimension inside of K count of x in terms of this Albanese mapping. So the theorem says that the codimension is always greater or equal to the dimension of the image of x inside of its Albanese variety minus the degree of the cohomology that you're looking at, minus I. Right? And so in particular, this means that if I take I to be less than the dimension of the Albanese image, then it says that this Si is a proper subset. And so this means that if you look at line bundles, sort of generally chosen line bundles or generic line bundles that are outside of this subset, the cohomology vanishes. So hence the name generic action. Okay, so I mean, you cannot expect a uniform vanishing statement, but at least you can get this type of thing that you have vanishing for generic choice of function in a certain range. Okay, so is the statement clear? Okay, so I mean, generally my point, what I want to do is explain how Hodge theory is used. So I thought I would give you very briefly a sketch of how this is proved, just so that you can see where the Hodge theory comes in. Okay, so just idea of the proof. So what their main idea was to look at the deformation theory of these groups. So in other words, you want to understand how hi, its dimension and so on, how that varies when you move L. In particular, when you just move L a little bit. Okay? So let's suppose we fix some particular point in X, and say at that particular point, the dimension of this space is equal to L. Okay? And then the first question is, if I just move L sort of infinitesimally in a tangent direction, how does this thing change? And so suppose I fix a tangent vector. I take a tangent vector V in the tangent space at the point L with mod of X. Well, this tangent space is actually just this cohomology group. This is isomorphic to just the first cohomology of the structure sheaf. Okay? And then Green and Lazarsfeld show that this V is tangent to the set Si, so it's tangent to if and only if the following thing happens. So you look at the complex that's built from taking the cohomology of this line bundle. And where the map is always given by cut product with this V. Yeah, so that since cut V has degree 1, so cut product twice is equal to 0, so that's a complex of vector spaces. And the statement is that V is tangent if and only if the cohomology in degree I stays n-dimensional. So if and only if this has n-dimensional, has cohomology in degree I, and least n-dimensional. Okay, so in other words, you're looking at this place here. Well, this is to begin with is a vector space of dimension m, right? So if the cohomology stays n-dimensional, it means that both the incoming differential and the outgoing differential have to be 0. Okay, so in other words, V is tangent if and only if cut product with V kills the cohomology of L, but it also kills the previous, the cohomology degree I minus 1. Okay? So it was equivalent to saying that V cut with I of x L is 0 and V cut H minus 1. I mean, the meaning of this is roughly that there are classes, those are the classes that that actually survive when you deform things in this particular tangent direction. Okay, and so now where's the Hodge theory? So Hodge theory is now used to analyze this complex. So in fact, this line bundle L, whose first term class is trivial, you can actually always realize it by choosing, when you think in terms of transition functions, it can be realized as by transition functions that are actually just complex numbers in absolute value. This is because of the term class equals 0. So if I write it in notation, it means that I can get it from a locally constant sheaf of rank 1 by just turning it into a vector bundle. Right? So this is the thing with the transition functions being constants, and then I just think of it as a vector bundle. So this here would be what people call a unitary local system.
So it's a flat line bundle with a structure.
It's a flat line bundle with a metric on it, and the metric allows you to reduce the structure to Euro form. Right? So a special case would be if I took the constant local system, I would just get the trivial bundle. Right? In that case, you have Hodge theory for the constant G, but in fact, you still have it in this setting as long as you have the flat bundle of the metric. So Hodge theory tells you that when you calculate the cohomology on X of this right here, then you still have a Hodge decomposition. So the classes here, they're represented by, again, some kind of harmonic forms. And you have a Hodge decomposition. Okay, and so now, if we look at the effect of complex conjugation, what complex conjugation does is it swaps this guy with its conjugate, where all the transition functions are conjugated. It swaps the line bundle, therefore, with its inverse. And it's going to exchange this group HQX omega px times L with HQX. So then I can take this whole complex here, and I can conjugate it, and because of the symmetry, nothing's going to change. All the dimensions and everything will stay the same. So if I conjugate my complex over there, I end up getting this kind of complex, and the differential is now wedge product with a holomorphic form. So where this omega is V bar, which can be thought of as just being a holomorphic form. Okay? And so then the place where this kind of inequality comes from is that this infinitesimal result tells you about the tangent space, right? So what you do is whether or not certain classes are annihilated by cut product with omega That's related to the rank of the Albanese mapping, the rank of the generic one. In other words, the dimension of the image. Right? Therefore, the dimension of the image of the Albanese mapping gives you some upper bound on how much stuff can be annihilated here by omega. That in turn gives you a bound on the dimension of the tangent space, and that in turn gives you a bound of the dimension. And so if you write it down carefully, you end up with this kind of inequality over there. Okay. So that's the first result. Let me tell you the second result. So the second result is similar to this Bourvil theorem, that you can actually describe the structure of these sets. So this is always a finite union of translates of subtori. And so again, the idea of the proof is, in this first step, we saw how you can use Hodge theory to establish a sort of infinitesimal deformation theory. Like it tells you what the tangent vectors are. And what Green and Lazarsfeld showed is that in this infinitesimal sense, there's no obstructions. So the obstructions vanish. Which means every tangent vector to Si can actually be extended to a whole line that's contained in Si. Okay, where by line I mean this stuff lives inside of some torus. So if you look inside the universal covering space, then that's a vector space, and there it actually becomes constant. Okay, and so then you're dealing with a subset of an analytic subset actually of a torus, which whenever you have a tangent vector actually contains the whole line, and then it's forced to be a union of translates of subtori. Okay. Let's see. Are there some questions?
Is this very sharp?
For individual i's not. I think if overall I, it's sharp. So there's always some arguments of shape.
If you allow yourself to consider various x and so forth, then you would not be able to get a result. It's sort of not about...
Yeah, it's not uniform over all x, that's right. So that's different from okay, so let me mention one result related to this statement here. So this Si of x, there's actually a conjecture by Bourvil about this, which was made at roughly the same time that Green and Lazarsfeld started proving these things. And so Bourvil conjectured that here, these translates, they should actually always be points of finite order. So the translates are always at points of finite order. And I mean, this conjecture was mostly based on this case of S1 that I just told you. I mean, Bourvil was one of the people who worked this out. And in that case, it turns out that even the extra points that are not explained geometrically, they're points of finite order. And so therefore, he thought should be true. This is known in the case when X is projective. So in the case when X is projective, this is okay. And it's a theorem by Simpson, and then independently also I have to think about it before.
So, but this is supposed to hold the projective very Taylor manifold?
Yeah, I'll get to that, sorry. Yeah, so let me say what's special in the projective case of that. So Bourvil he conjectured it actually for compact Kähler, because the other thing is true in the compact Kähler case. But people can only prove it in the projective case. And the reason is, what makes projective special is that then X is actually algebraic. So it's actually given inside a projective space by polynomial equations. And then what you can do is, you can fiddle with the coefficients of the polynomials and actually make sure that, with a little bit of care, if you choose them right, you can actually choose the coefficients to be all rational numbers. Okay, which means in algebraic geometry language that you can assume that this X is actually defined over the rational numbers. And then you can use methods from number theory. So what Simpson did after, so you reduced to the case where X is defined by equations of coefficients in Q, and then Simpson used some methods from number theory to prove this statement. And Pink and Gerster, they used methods in characteristic Q.
Is this Carlos Simpson or?
This is Carlos Simpson, yeah.
We have a statement about subtori. For rather generic X, will there be rather few subtori?
Yeah,
complexori? So
yeah,
that's sort of very rare to happen.
That's right, yeah. So if X is pretty generic, then in fact this says that these sets are either all of Picnor or they're just points. And then Bourville would be predicting that the points are actually points of finite order.
A lot of times those problems become harder when there might be some but not many.
Okay. So this theory that I've explained, it had a lot of applications over time. Like, so there's a couple of geometric problems that somewhat unexpectedly can be done by this kind of method. So I will say something about some application like this later. But my main point will be from now on just this. So this is how it was 25 years ago, and I want to explain how our understanding of these theorems has changed over time. Okay? So let me first explain that there was one new point of view on these theorems, which is due to Hacon, Christopher Hacon, and then also Pareschi and Popa. But this is now all in the projective case, so I will assume from now on that X is projective. And then, time permitting, I will try to come back at the end to the compact Kähler case, what we can say about that.
So Bourville's conjecture said might suggest that it's actually a subgroup. Is that also true?
No, that's not true.
Okay. And has there been any effort to try and count the number of pieces?
No, there has been no effort.
Is that probably impossible?
You might find some interesting, there could be some interesting meaning to this. I mean, generally people take the point of view that, for example, the isolated points, you don't really understand them geometrically. And we have some hope with positive dimensional components of relating them to the geometry of X, but the isolated points are kind of mysterious. Okay, so I will assume now that X is projective because I have to use some algebraic methods. And so the first thing is, we start from the observation that, again, by Serre duality, this group is isomorphic to, so that is the dimension of X. Okay, but this is the canonical bundle. And so with the obvious kind of notation, I could also say this as an identity of these sets, right? So this kind of cohomology will be non-trivial exactly when this kind of cohomology is non-trivial. So this means that, so I will write it like this. Okay, this means that you look at the cohomology of the canonical bundle, but tensor with various line bundles. And then this says that these sets are basically the same up to like this, replacing L by L inverse. Okay, so this is one thing. The reason for looking at the canonical bundle is that algebraic geometers have more results about the canonical bundle. So, okay, the other observation is that the line bundles of degree 0 on X, they actually all come from the Albanese variety. Okay, remember that we have this. So any line bundle of degree 0 on X is actually coming from this now abelian variety, in this case when X is projective. They're actually all pulled back. So then to an algebraic geometer, it naturally suggests that instead of trying to compute the cohomology of X, you should try to push it down to L with X and see what you can do there. Okay, so then if I want to calculate, say, this kind of cohomology group here, the natural thing to do is push it down by this Albanese mapping and calculate it there. And in fact, then something very nice happens, which is that this thing can be completely understood in terms of information down on X. Here, so the actual number doesn't matter. Okay, so I mean the general principle is whenever I'm in this kind of situation where L actually comes from downstairs, I can push it down and I can calculate this in terms of the things on the right hand side. But usually it's by some complicated formulas, like some spectral sequence or something. And in this case, what's special about the canonical bundle is that this actually splits up and the cohomology is just the direct sum of all of these pieces.
So the spectral sequence degenerates all
the spectral sequence degenerates, yes. So this is some result by polar. So this is some Polar's theorem about X.
Don't worry, nobody gets the accents in your name, right?
All Hungarian accents go that way.
Okay, that's good to know. Okay, so what this does is it puts some emphasis on these kind of sheaves here. Okay, so it puts some emphasis on these. So these are certain coherent sheaves on the abelian variety. And what one can do is, you can understand actually all the theorems about that we and Lazarsfeld prove. You can all reformulate them in terms of these sheaves. So they can all be stated by saying that these sheaves on the abelian variety, they have some spectral properties. Okay, so for example, these sheaves are what's called GV sheaves. So they satisfy also some inequalities. So if I use the obvious notation again, I look at the codimension of, again, these kind of sets. Okay, so by this now I mean that I look at these sheaves on half of X. Again, I look at the sets where the cohomology is non-trivial, like tensor by randoms. And then these guys now have this uniform bound that's just independent of any geometry. It's just always the degree of the cohomology. Okay? And so this kind of thing, which is provable by different methods from what Green and Lazarsfeld used, this will actually imply the inequalities in the Green-Lazarsfeld theorem. Okay? But because this statement is uniform, it kind of gives a better explanation for what's going on.
You already get some information just from the fact that these sheaves are supported on a small set. Typically, the Albanese map is not typically surjective, so.
Yeah, that's right. So this will give you some bound on the range in which these things can be non-zero. Yeah. Okay, so the new point of view is that instead of thinking of this as being a relative on X, we think of it as being a statement about special sheaves on the varieties. So here, people develop many other results. Like, so you can prove a bunch of other interesting results about these sheaves, and from that you can get then some nice applications on projective varieties. So I will tell you one nice application. This is the theorem by Chen and Hacon. And so what this theorem does is it characterizes for you abelian varieties among all possible projective varieties, up to birational equivalence. Okay? So this is the birational characterization. So again, this is something very popular in algebraic geometry because, for example, there's many classical results about surfaces that you can detect whether a surface is birational to an abelian surface or not by just looking at certain numerical invariants. And this Chen-Hacon theorem says that the same can be done for abelian varieties in general. So it says if you take x degree smooth projective, so projective manifold, and then suppose that the dimension of x is equal to 1/2 the first Parechi number, and also the so-called Curie genera equal to 1. Where Pm of x is the dimension of the space of sections of the nth power of your canonical bundle. Okay? So any abelian variety will satisfy these conditions, because in abelian variety, this bundle is just trivial, and so you're just looking at sections of the trivial bundle. And then in fact, they're birational invariant. So anything that's generically isomorphic to an abelian variety will also have the same. And the Chen-Hacon theorem says that, in fact, that then x is birational. And of course, in fact, to Albanese effects.
So this is a colloquium. It might be a good idea to define the term abelian variety, projected manifold that is a complex storage.
Yeah, that's right. Sorry. Yes, so abelian variety is. Right, so in fact, what you end up showing is that the Albanese map from x to alpha of x is actually surjective, and it's in fact generically an isomorphism. Okay, so therefore it's birational. Right, so this is a consequence of the formalism that grew up around these results in the projective case. Okay. All right. So now, at this point, I actually enter the story. So I haven't entered the story yet, right? So I entered the story as being a new postdoc at UIC who just learned a lot of Hodge theory in graduate school and kind of wanted to show people that this is useful somehow. And one of the people over there named Popa, Popa, he was also at UIC, and so he's very charismatic and very good at getting people interested in the problems that he's interested in. And so then I started thinking about this kind of topic from Hodge theory point of view. And so what we started doing is we went back to this relationship between these kind of groups and these topological groups. Right? So we saw earlier that this kind of thing will occur as one of the summons in the Hodge decomposition here. Now, the method that was successful in this new point of view was don't calculate things on x, but push it down to the Albanese variety and calculate it here. And so we tried the same thing for the topological point of view. Okay, so again, this U, which is one of these unitary local systems, it actually also comes from x, because U is actually corresponding to just a character of the fundamental group, which therefore sees only the abelianization of the fundamental group, and that's the same on alpha factor as well, because they have the same H1. Okay, and so then again, the natural thing to do is when you want to calculate the cohomology of this, you actually calculate it down on alpha x. And again, it turns out that something very similar happens. So you can compute this cohomology here in terms of cohomology groups downstairs on alpha x. So just like this. And now there's some terms that I'll call kg. And k sub jk, where the kjk's are perverse sheaves. Okay, so in other words, there are systems of coefficients for computing cohomology that generalize local systems. That generalize locally constant sheaves. Okay, and so this identity here, this is known as the decomposition theorem. Okay, so this is a famous result in algebraic geometry that says these kind of topological things, they have this property that when you push them forward by some map that's projective, then actually, again, all the spectral sequences degenerate, and the cohomology breaks up into a collection of summons like this.
What's so perverse about these sheaves?
Yeah, they're not right. I mean, so let me say this here. So what are they actually? So each of these JK lives on some subvariety, lives on an irreducible subvariety, say yjk, inside of alpha. And in fact, it's not a sheaf, but it's actually a whole complex of sheaves. So in fact, it's a complex of sheaves like this. So this is a complex of so-called constructible sheaves. Okay?
So that last thing is followed by 0, or so these are...
Yeah, so the complex is like this. Okay, so a constructible sheaf is a generalization of a locally constant sheaf. It's a sheaf of vector spaces, finite dimensional vector spaces, but it's not locally constant. Rather, there's a stratification of your space so that on each stratum it is locally constant. But the ranks may not be the same over different strata. And so the way you think of this perverse sheaf is this guy here, which for conventional reason is put in negative degrees. This is generically a local system. And all the higher order, all the other terms in this complex, they're also constructible sheaves, and they kind of serve to correct this and give this individual guy here better properties. So the whole complex together consists of this main part plus these correction terms, and altogether it ends up having better properties than each term just by itself. Okay, so this is a way of basically taking a local system or locally constant sheaf on an open set of yjk and extending it to all of yjk in a way that it gets good properties. And these are the kind of things that occur.
So what happens to the end? I mean, in this expression, you don't have a super index on kjk. So when you're computing the cohomology, is it the direct sum, or is it grade? What?
When you calculate the cohomology, this.
No, I mean, so here's an expression.
You really think of it as a complex. So then you have to use some algebraic formalism of calculating cohomology. So you don't take here, you calculate it by some spectral sequence, or replace the sheaves by some nicer sheaves for which the cohomology can be defined more easily and then calculate it like that. But yeah, so what's happening is you take a relatively complicated space with a simple system of coefficients and you turn it into computation on relatively simple spaces, because these guys here, they're just subsets of an abelian variety, so their geometry is relatively simple. But it comes at the cost of introducing these more complicated systems of coefficients. Okay? You simplify the geometry, but you get more complicated coefficients. And so then, motivated by this, Michna and I, and then later I by myself, we did a general study of these kind of coefficients on abelian varieties. So maybe I just tell you some sample results. Maybe go in this direction, just so that you can see the analogy with the Lazarsfeld theory. So this doesn't have to be the Albanese variety now, right? We can just, now in general, we take one of these perverse sheaves on just an arbitrary projective torus, an arbitrary variety. So let's say I take A to be an abelian variety. And K to be one of these perverse sheaves. So for example, one of the ones over there. And then I'm going to look at the space of just local systems of rank 1. So this L is a Okay, so in other words, so like one of these views, for example, but not necessarily unitary. So in other words, this L is just, it's a character of the fundamental group of A. Now the fundamental group is just Z to the 2 times the dimension. So this is actually just as a space, it's just C star to the 2 times the dimension. Okay, and then again, we're going to look at these kind of loci. So just a set of such systems where the cohomology of the Pareschi twisted by that is non-zero. And so then we get some analogs of the green Lazarsfeld type results. So the first thing we can show is that the codimension of these sets is always greater or equal to 2 times A. And here I put absolute value because these complexes, they live in negative degrees. So the cohomology can actually be in negative and positive degrees. Okay, so here this I can actually really be considered. Okay, so this is like an analog of the kind of inequalities that we Lazarsfeld get. And we also get an analog of these structural results. So these things here, they are always finite unions of translates of subprime. And in fact, if K comes from geometry, so for example, like the Pareschi in the decomposition theorem over there, then these translates are by points of finite order. And then from these theorems, it turns out you can actually, if you put them together with some Hodge theory, you can rederive, for example, the green Lazarsfeld results. So, and for other things that we can do is we get from this a new proof of O'Neill's projective. It doesn't use any other theory.
Again, in the projective case.
In the projective case, yes. I mean, everything is still in the case when A is divided. Okay, so, yeah. I mean, let me just say briefly. So, the methods here, they're completely different. They're not Hodge theory anymore, but it's proved by exploiting the so-called Riemann-Hilbert correspondence. So, there's another equivalent point of view to these Pareschis, which is in terms of so-called D-modules, which are some kind of algebraic version of systems of differential equations. And there's a correspondence called the Riemann-Hilbert correspondence that says that to every Pareschi, you have one of these systems of differential equations associated with. And by comparing these two different points of view, like this topological point of view and this analytic point of view, you can get some interesting constraints on the structure of these sets. And so this is, for example, how the second thing is proved, by making this comparison. Okay. Okay, I don't have very much time, so let me just, in closing, say a few words about the compact Kähler case. So this, what this shows is, this was sort of our new point of view, that the green Lazarsfeld type of results, they're not really results about X and Hodge theory and so on, but they're really results about special objects on abelian varieties. Right? So the source for all of this behavior is somehow the fact that you're dealing with abelian varieties, and for example, that abelian varieties are groups and things like that. However, in the process, we completely lost one aspect of the original result, which is the original green Lazarsfeld stuff was on compact Kähler manifolds. And now we're just in the world of only projective varieties. Okay, so how do we go back to compact Kähler? so what happened there was, I was at a conference in Notre Dame at some point, and some graduate student by the name of Wotong Wang, he came up to me, and he asked me whether I had ever thought about this Bouvier conjecture in the compact Kähler case. Okay, so I said, yeah, I have, as it turns out. So I just made this, I just found this new proof in the projective case, and it doesn't use any number theory anymore. So I have some hopes that maybe it can be generalized to the compact Kähler case. In fact, I have some ideas, but the problem is there's a lot of formalism in it, and the formalism somehow has only been developed on abelian varieties. And you would need the same formalism on compact tori. And so I think probably at some point in the future I can do it, but it's going to take me a long time. Okay. So then I didn't hear from him for some time, and then at some point, maybe 3-4 months later, he sent me an email with a preprint, and where he actually sort of figured out the answer. So he was fortunately not deterred by this very technical answer that I gave him. And so what he had is, he had a very, very nice new idea, which is that compact complex tori. So I used to think that compact complex tori are very different from abelian varieties. And in some sense they are. But his great idea is that they are very close to abelian varieties. If you look at perverse sheaves. If you're interested in studying perverse sheaves, there's very little difference between arbitrary complex tori and abelian varieties. So I'll just tell you sort of what the gist of the idea is, okay? But this is a very, very powerful idea that he had. So, for example, let's suppose I take a torus of dimension at least 2. Yeah? And suppose I take a generic, so with a generic complex vector. Okay, so then in fact, this thing has no subvarieties, no interesting ones. The only subvarieties are T itself and points. So now, if I have one of these perverse sheaves, it's going to live on some subvariety. That subvariety could either be a point, in which case it's trivial, or it could be, well, the entire torus. And then in that case, this perverse sheaf is generically a local system, and the points where it's not a local system are subvarieties. So they're, again, just finite sets of points. But a local system is, since it has to do with representations of pi1, it extends over points of codimension 2, right? Because the fundamental group doesn't see codimension 2 or higher stuff. So actually, in this kind of case, any perverse sheaf on T either lives on a point, or it's actually a local system of all of T. So it is either on a point, or it's a local system. And in general, he showed that for any compact complex torus, you can always find a map to an abelian variety, so that up to tensoring by local systems, your perverse sheaf actually is the pullback of a perverse sheaf on the abelian variety, basically by amplifying this kind of observation. And so then, of course, everything immediately reduces back. All the cohomology computations immediately reduce to the case of abelian varieties, right? And so in particular, any result that we can prove for abelian varieties, we now get almost for free in the compact Kähler case. So for example, Wang used this to prove Bouvil's conjecture in the compact Kähler case, just by reducing it to the abelian varieties case. And in some ongoing work with Pareschi and Popa, we're using, again, the same idea to get this Chen-Hacon theorem, this characterization of abelian varieties for compact complex tori. So exactly the same numerical conditions will characterize compact complex tori among all compact Kähler manifolds up to bimeromorphic equivalents. Okay, so this is some of the most recent development in this subject. Okay, thanks very much. Yes.
So I guess I was tacitly assuming that X was always a smooth variety, but does it make a difference? If you allow X to have certain kinds of singularities, does the theory go through?
You can allow certain singularities, but then you shouldn't be working with these trivial coefficient systems. I mean, the way you allow singularities is always that you then have to put more complicated systems of coefficients. So, for example, here instead of in the topologist language, instead of working with usual cohomology, you have to work with intersection cohomology, right? Instead of with a constant local system, you have to work with a perverse sheaf, which is the so-called intersection context. If you make those changes, then the same theorem will work for those cases. Yeah.
So, roughly speaking, how do you see this sort of translation by finite order points using that point of view?
How this is proved?
Yeah, you said in the projective case you use some number theory, but in your
yeah, that's right. So here, once you have this statement that they're all actually translates by subtoire, you then know that whenever you have one of these components, it's actually related to some map from the abelian variety to some lower dimensional abelian variety. If you play around with these maps, then you end up reducing it to just a very special case. Like just the formalism that we have, it reduces this problem to just a single special case, which is that you have a local system of rank 1, which is unitary, but it also occurs as a direct summand in a local system with integer coefficients. That's the kind of situation that you can reduce the problem to. And then in that case, the claim is that if you look at the eigenvalues of the monodromy, they're actually roots of unity. Right? And so then it follows from this Kronecker theorem that if you have complex numbers if you have algebraic integers, all of whose conjugates have absolute value 1, then it's a root of unity. So that's sort of the only number theory that ends up being used.
No, I was saying, isn't that number theory at the same time?
Yeah. Sorry, I stole your job. Yeah, so it is number theory, but it's little enough number theory that you don't have to assume it's projection.
Questions? If not, this ends, please.